In this video, we'll take a look at 36 typical exam questions that you would see on a second semester chemistry final. And as usual in my videos, I will have timestamps in the description for each question type and a short description of what that question is asking and assessing what type of topics there are. I will also include a general list of the topics that are covered here and with timestamps for that as well. So with that, we will get right into it. So this first question is asking us to predict the strongest UV absorption that we would see for the following compounds. So first we need to kind of observe what's the difference between these two. And the first thing that I notice is this is a conjugated diene, and this is not. These are isolated double bonds. So what this implies, this has direct implications on the type of UV absorption that it has. So in general, a 1,3 conjugated diene, like is the case here, the UV absorption is approximately 220 nanometers, give or take depending on the specific compound. And in a question like this, they really want the approximate value. So 220 is about accurate. And then for isolated pi bonds, it is approximately 165 nanometers. And unfortunately, these are just kind of values that you need to have memorized. The main thing was being able to recognize that this is a conjugated diene versus isolated diene. And the way to recognize that, conjugation has this pattern of pi, sigma, pi, or double bond, single bond, double bond character here. And this is what we mean by conjugation, and hence why it has a 220 nanometer wavelength as a strong UV absorption. All right, so here we have our second question, and we are asked to draw all the possible resonance contributors for the following compound. And so the first thing I notice is we have this nitro group with the NO2, this negative charge on the oxygen, that can easily delocalize in a resonance structure through the nitrogen, like drawn here. Right, now this is possible at all of the possible resonance structures, so I'm only going to show this as representative of all of the oxygen contributors, because we're going to have delocalization of these pi bonds as well. So you could get possible permutations where you have the carbocation and this particular negative charge on the oxygen, or the carbocation with this negative charge on the other oxygen. So to avoid drawing all of those as their equivalent, we're only going to show the distinct ones. So this is the case here for this first oxygen. Then you can delocalize the pi bond here. For example, this will put the carbocation at the top carbon. I forgot the methyl group here. Right, this will put the carbocation at that top carbon there, since this carbon is now electron deficient up at the top because we've moved the pi bond. And now what I was trying to mention with the oxygen here is you could have a similar resonance structure now where this negative charge moves up to the oxygen. And while I'm at it, we might as well just draw it and show what I'm talking about. So you can have this occur as well, getting another possible permutation. It's a different resonance structure, right? And then you can have another resonance structure with the carbocation, once again, shifting with the pi bond shifting like so. And then the negative charge on the oxygen can shift again. And this is all the possible options that we have here as far as I can tell. Let's look here. The carbocation can move twice. It has moved twice. The oxygen can only move once, but it can move with all of the possible carbocations. So we have the original with the moved oxygen. Then we have the first carbocation with the moved oxygen, second carbocation, and the moved oxygen. That is all possible resonance structures for this question. if resonance structures are confusing for you, I will have a link in the description to the video where I work through resonance structures in a general sense, but hopefully that was clear. Now, question number 3, we're asked to rank the following carbocations in order of increasing stability. So let's label these somehow. Let's call it carbon molecule 1 to 4 from left to right. So if we look at these, molecule 1 is a tertiary carbocation, 2 is a secondary, 3 is also a secondary, 4 is a primary, right? Now how we do that is we count the number of carbons bound at the carbocation. So this carbon here is bound to one carbon up and to the right, it's bound to another carbon down here, and then bound to another carbon to the left. So that's 3, that's why this is tertiary. We'll do one more like that to show how you do this. So this carbocation here is bound to one carbon to the left, another carbon to the right. So that's 2 total carbons for a secondary carbocation. Now, what is the main thing that you need to know here is that stability for carbocations increase with the substitution that you have at the carbon through a phenomenon called hyperconjugation. So the tertiary carbocation here is going to be more stable than any of the other options, and increasing, like it'll propagate down. Secondary is less stable compared to tertiary, and primary is less stable than secondary. So here we are asked to rank in order of increasing stability. So 4 is the least stable, 2 and 3 are equivalent, and then 1 is the most stable. All right, here we have our next set of questions. So question number 4 asks which resonance structure is more contributing, and then explain why. So for contributing resonance structures, you're looking for the most stable. So most stable resonance structure is therefore more contributing. So what are some factors that increase stability? Well, if you have a charge, so negative charges prefer electronegative atoms, if possible. Neutral compounds are more stable than charged. This is listed in no particular order, by the way. And then you need the octet rule satisfied at all atoms. Well, I should be more specific on all atoms that require an octet, because for instance, like boron, you won't have an octet. Sulfur could have an expanded octet, things like that. But like things like carbon and oxygen and nitrogen, they need to have an octet, or you're not going to have a significant contributing structure. Now, what else? You could have something that's aromatic and things like this, but for this sake, this is good enough here. So the most fundamental rule is the octet rule. Then neutral compounds are more stable, and then negative charges. So this is kind of the precedence that you should look for. So here in our 2 resonance structures, all atoms have an octet. We have this oxygen has 2 lone pairs that's not drawn. We have the carbon with 4 bonds there, 1 to the nitrogen, 3 to hydrogens, 3 different hydrogens, same at this other methyl group here. So this seems extremely stable because it's neutral, octet rules followed, so that seems pretty significant. If we look at the other structure, we have a negative charge on the oxygen and a positive charge on the nitrogen, which this isn't unreasonable, like this is a suitable resonance structure to draw, but this is not going to be significantly contributing because of the di charge compared to neutral. So this is much more contributing. That will be the answer. This neutral state is going to be far more contributing to the resonance here. All right, moving on. Question number 5 asks, rank the following dienophiles in order of decreasing reactivity towards Diels-Alder. So dienophiles are preferred to be electron poor. So I'll say dienophiles are better if they're electron poor for Diels-Alder. So now we have to look at our molecules here and determine which one is more electron poor. So for something to be electron poor, it needs to have electron withdrawing groups. So the dienophile with the most electron withdrawing groups will be the most reactive. So I write most electron withdrawing will be most reactive. I mean the dienophile with the most electron withdrawing groups will be the most reactive. So let's go through one at a time and assess the groups and see if they're electron withdrawing or donating. So looking at this first structure here, we have a carbonyl, which has a partial positive on the carbon, partial negative on this oxygen and the other oxygen, but I'm not going to draw that. So here we have a partial positive adjacent, so this is strongly electron withdrawing. The positive charge wants to be stabilized in essence, so if it withdraws electrons from that pi bond, that will stabilize that positive charge, making it electron withdrawing. That's the same for the other carbonyl here, exactly the same. So strongly electron withdrawing groups on either side. Now, if we move to the other side here, we have a ketone, which has a similar effect to the carbonyl, or the carbonyl has the same effect, but similar to the carboxylic, is what I meant to say. So this is also electron withdrawing. But now what about the other side? The other side, we have a methyl group. So this is electron donating through hyperconjugation. The same phenomenon that stabilizes carbocations is present here, stabilizing the diene and making it more, the dienophile rather, making it more electron rich, which is not favored if you want a successful Diels-Alder. So this is probably not our answer, this second molecule here. All right, then if we move on, we again have electron withdrawing, the carboxylic acid group here, but then we have two hydrogens. These are just kind of neutral. They're neither electron donating nor electron withdrawing. They're just there, and they don't have a significant effect here. So if we're comparing the second and third molecule, the third one would be more reactive than the second one. Moving on to the last one, we have two methyl groups. These are both electron donating, so this is going to be our worst dienophile towards Diels-Alder because it is very electron rich. So let's label these molecules in order, left to right, 1, 2, 3, and 4. We are asked to go in order of decreasing reactivity towards the Diels-Alder, so most reactive first, and then in decreasing order, so less than. So molecule 1 is the most reactive, followed by 3, because 3 only has the electron withdrawing group, not donating. 3 is greater than 2, which does have the electron donating group. And then 4 is the least reactive because it has the di-electron donating groups. So that will do it for this question. Move on to our next one. All right, question 6, we are asked to determine if the following molecules are aromatic. So the rules for aromaticity, I'll write over here. There are 4 of them. So 1, it must be cyclic. 2, the structure must be fully conjugated. 3, it must be planar. And then 4, you need to follow Huckel theory, which is that you need 4n plus 2 pi electrons, where n is a 0 or integer. So in essence, you need 2 pi electrons, 6 pi electrons, 10 pi electrons, and so on. So this essentially boils down to you need an odd number of pi bonds, but you also have to remember that you can sometimes use lone pairs as pi bonds if their resonance creates a pi bond, right? So we'll look at that, a couple examples like that. So let's go through these rules here. Looking at molecule 1, it is cyclic. It doesn't really look to be fully conjugated because we have this sigma-sigma here, right? Those 2 single bonds in a row. But notice the pi bonds can delocalize like this. So what this does is put that positive charge at 4 distinct carbons, making it such that the totality of the resonance hybrid is fully conjugated and therefore follows Huckel theory rule. follows the aromaticity rule, which is the same for planarity. All carbons are sp2 hybridized, so they follow planarity. So now, does it have a Huckel theory number? Well, it has 3 pi bonds. That's 6 pi electrons, so this is aromatic. Okay, moving on to the next one here. This is a case where it appears that we have 2 pi bonds, so you would just say, based on Huckel theory, that this is not aromatic. But you have to, again, consider the resonance. So now a lone pair becomes a pi bond, so I'll draw this one resonance structure here. So that lone pair has become a pi bond. So now you have to count that lone pair as part of the total pi electrons. So in essence, it has 6 pi electrons or 3 pi bonds, because sometimes that lone pair is actually a pi bond, depending on the resonance structure that you're in. And remember, these actually exist as a resonance hybrid. So in reality, that pi bond just has partial lone pair character and partial bond character, double bond character. So in essence, that means that it follows Huckel theory. It is fully conjugated for the same reason that the first one is. The resonance allows for this conjugation. Fully planar, again, for the same reason, due to the resonance. And then, of course, it is cyclic. So this is also aromatic. Okay, we move to this third one here. We have an sp2 lone pair. This cannot resonate into the ring because it's sp2. It's orthogonal to the orbital is orthogonal, so it's not possible to resonate in. So you only count the pi bonds. There's 3 of them, so it's 6 pi electrons. That is a Huckel theory number. It's also cyclic. It is fully conjugated. It is fully planar. This is aromatic. All right, now let's move to the next structure here. So this has 4 pi electrons. It is fully planar, fully conjugated, again for all the other reasons that we mentioned due to resonance in these things. So this is not aromatic because it doesn't follow Huckel theory. Right? 4 pi electrons is not a Huckel theory number, therefore not aromatic. All right, here we have our next question. We were asked to predict which direction the equilibrium lies. So this is a typical keto-enol tautomerization. And in general, in keto-enol tautomerization, the keto form is going to predominate because of the added stability of the carbon-oxygen double bond compared to the carbon-carbon double bond. But sometimes there are special factors that stabilize the enol. The special factors that stabilize the enol, in a general sense, there's probably more than this. This isn't comprehensive, but there's 3 that I can think of. 1 is aromaticity. 2 is conjugation. 3 is intramolecular hydrogen bonding. So in this case, this enol has conjugation between the carbonyl and the ene, the alkene, and it also has intramolecular hydrogen bonding. So let's get rid of this hydrogen here and draw it so we can show the intramolecular hydrogen bonding, like there. So that stabilizes this molecule a little bit more in addition to the conjugation. So due to those 2 reasons, the enol is actually going to dominate here because you have intramolecular hydrogen bonding and you have full conjugation. So the equilibrium lies to the right or in the forward direction. All right, so here we have our next question. So we are asked to rank the following in order of increasing reactivity towards nucleophilic addition. So what we have, first of all, is to recognize what is the difference. The difference is the leaving group, right? So these are all going to be nucleophilic acyl substitution with a nucleophilic addition step preceding the substitution. So the leaving group is in essence what's changing here, and I'm circling each leaving group. So remember that leaving group propensity is due to conjugate base strength. So leaving groups are better if they are weaker conjugate bases. What that means is that they are stable as a conjugate base. They are stable, holding that negative charge, and therefore they will do that and become a leaving group. So then we need to assess the relative acid strength of the resulting species here, right? So we have Cl minus is our leaving group, and I'll draw this acetate, then the methoxide, and the amide, right? So all right, so the question is, what are the corresponding acids? So we have HCl, acetic acid, methanol, and ammonia. All right, so HCl is a really strong acid, so we expect Cl minus to be a really good leaving group, very weak conjugate base. Acetic acid is relatively strong, so its conjugate base acetate is also relatively good a leaving group. Methanol is a very weak acid, relatively speaking, so its conjugate base is going to be pretty strong. Ammonia is an extremely weak acid, so NH2 is an extremely strong base. So this list then 1, 2, 3, 4 like this in terms of we're going in increasing order. So the weakest is going to be 4, which is less than 3, which is less than 2, which is less than 1. All right, so that is that one. Moving on to question number 9. Here we are asked to draw all possible enolates. So the enolate is when you have alpha protons and you remove those. So I'm drawing in the alpha protons. And this one, alpha means the position adjacent to a carbonyl. This compound has no alpha protons because aldehyde protons are not considered alpha, and then this position is not does not have any hydrogens there. It's fully substituted. Now, this last compound does have hydrogens in the alpha position. Remember, the alpha hydrogen must be bound to the alpha carbon, so the carbon adjacent to the carbonyl. Right. So if we remove these, any one of these, let's just start with this one, you're going to get this particular enolate. Right, so that's 1. You could remove the other 2 hydrogens at that spot, but it will give you the exact same enolate. Okay, now we can remove this one here. And now this one's kind of unique because you can form a cis or trans isomer here. So this one is cis, but you could also have the trans. Which would look like this. Assuming I counted the carbons right there, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, that is right. So that's the middle one, and then you can remove, so we removed this one and this one so far. You can also remove this last one here. And this one can also be cis or trans because it is internal. So since this one doesn't have any, I'll move over here a little bit to draw this. So this one is cis. Oops. And then this one would go down here. Oops, 1 too many carbons. So that would give you the trans. So and if you're wondering how I know if those are cis or trans, you have to assess the priority on either side of the pi bond. So if you look at this side, oxygen is going to get higher priority than the methyl group, the methylene group, just the carbon there. So that gets priority. It's oriented up. Then we look at the other side, we just have a hydrogen and then the alkyl group. So the alkyl group will get priority. Those are both up relative to the pi bond, so they're cis or Z. Then if you look at the other one now, we still have the oxygen being higher priority. Now the alkyl group is down versus up, so that is trans. Same argument for the other one. Now this middle molecule has no alpha proton, so there's no enolates that you can draw. This one, fortunately, there's only one you can draw, so you remove this proton and you get the enolate, which looks like this. All right, and that is that one. All right, next we are asked to determine if the following sugars or carbohydrates are hexoses or pentoses. So this is simply talking about the number of carbons that are present. A hexose will have 6 carbons, a pentose will have 5 carbons. So here we have 1, 2, 3, 4, 5, 6 carbons going from top to bottom. That is the same for the first two, they both have 6. So they're both hexoses. Okay, moving on to the third and fourth one, these only have 5, so these are both pentoses. Now, the part 2 of this question is aldoses or ketose. So this refers to the functional group that you have in either case. So aldoses have an aldehyde and a ketone, or ketoses rather, have a ketone. So here CHO, that's an aldehyde group. CHO, that's an aldehyde group. So the first and fourth one are aldoses. And then the second one has a ketone here. The third one has a ketone here. Those are both ketoses. All right, and that is that one. Moving on. Here we have question number 11. So determine the number of chiral centers in the following sugars or carbohydrates, and then determine the number of possible stereoisomers. So here, in a general sense, the top and bottom carbons are almost never going to be chiral because they're either going to have a double bond, like is the case with an aldehyde, or they're going to have 2 hydrogen groups. So in essence, this can boil down to just counting what is in between the terminus, especially when you have an aldose. So here it's 1, 2, 3, and 4. But to be most accurate, you should always check that you have 4 different substituent groups at each chiral center, and that will give you the number of chiral centers. So the reason this doesn't work for the second one now is because you have a ketone in the middle, so you cannot count that one as chiral because it only has 3 different groups because the carbonyl takes up 2 spots, basically 2 of those bonds. So this is 4 chiral centers. This one has 3. Moving on to this one, it only has 2. Again, the termini, I guess, has 2 hydrogens at both of those carbons. So you don't count those. Those are not chiral. And then the ketone is also not chiral, so only those 2 positions there have 4 different groups. And then this last pentose has 3 for the kind of similar reasons as the first one. Now, to determine the number of possible stereoisomers, you use this formula 4 to the n, where n equals the number of chiral centers. So let's call this molecule 1, 2, 3, and 4. So molecule 1, we'll write it over here in terms of number of stereoisomers. Molecule 1 is 2 to the 4, which is 16. Molecule 2 is 2 to the 3rd, which is 8. Molecule 3 is 2 squared, which is 4. Molecule 4 is 2 to the 3rd, which is 8. All right, that's how you can go about assessing the total number of stereoisomers without drawing them all, because that would be a nightmare for when you have 4 chiral centers. 16 possibilities is quite a lot. You can easily miss one. All right, moving on to question number 12. Here we are asked to determine the absolute configuration at each chiral center in the following sugar. Okay, so a couple things that we should focus on. One, this is not symmetric because where the symmetry is broken at the two terminus positions. So because of that, this is completely chiral. Each of the possible centers are chiral. So there's 4 options that we have to address. Secondly, Fisher projections have the following general structure in terms of 3-dimensionality. So if a hydrogen is on the horizontal, then you have to invert what it appears to be, because it's just like if the hydrogen was on a wedge in a standard skeletal structure. Okay, so that's what we need to keep in mind. So now let's assess priority at each position. So we'll start top down. So this carbon is bound to a oxygen, a carbon, a hydrogen, and another carbon. So oxygen gets the highest priority in that comparison. Then we have to move to the next position, right? So our carbon and carbon are the same. So we need to consider what that is bound to. So this carbon down is bound to an oxygen and another carbon. This carbon is bound to 2 oxygens. Because remember, we count double bonds in Conjugated rules as additive, right? So it's as if it was bound to 2. Then we're comparing a hydrogen to a carbon, so the hydrogen is the lowest priority. So this looks like S, right? It's going counterclockwise. So that would be what it is, as long as the hydrogen was on the vertical. It is on the horizontal, so it's actually R. Now, this little trick I came up with the other day for how to remember R and S. So when you draw an R, right, the first time that you're moving to the right or the left in drawing capital R, you move to the right. So that is clockwise. So this is how I remember now that R is clockwise, and opposite for S. You move to the left when you write an S, so that is counterclockwise. So that's a little trick to help you remember that. All right, so this first position is R. Okay, now let's move to the second position. So this oxygen gets the highest priority. Then we are comparing a carbon bound to an OH versus a carbon bound to an OH, compared to a carbon bound to an OH versus a carbon bound to 2 OHs. So to 2 oxygens rather. So this second priority goes at the top, and then at the bottom. And then the hydrogen, of course, is last. So this appears to be S again, but the hydrogen is on the horizontal, so it's R. So I'm kind of speeding through this a little bit more here. It gets a little bit messy when you have so many different positions that you need to consider, but hopefully it's as clear as possible. So this carbon now is our next center that we're looking at. So again, the oxygen gets the highest priority. Then we're comparing a carbon bound to an oxygen versus a carbon bound to an oxygen. That's the same. Then we move again. We have a carbon bound to 2 hydrogens and an oxygen versus a carbon bound to an oxygen and a hydrogen. So the up position gets the second priority and down gets the third priority. That looks like R. So the hydrogen is on the horizontal, so it's actually S. Okay, let's move on to the next one. So oxygen gets the highest priority. Then we're comparing a carbon bound to 2 hydrogens and an OH versus a carbon bound to an OH and another carbon. So up gets the next priority, and then down. So that looks like R. The hydrogen is on the horizontal, so it's S. So I'll redraw this without all the stuff. Right, so this is R, R, S, S. All right, that is the correct assessment for this particular sugar. All right, moving on. Here we have our next set of questions. So question number 13 asks, determine the absolute configuration at each chiral center in the following amino acids. So we only have one chiral center in all of them. So let's assess the central alpha position. So we're comparing a carbon to a nitrogen to another carbon. The nitrogen gets the highest priority. Then we're comparing a carbon bound to 3 oxygens in Conjugated Alkenes rules versus just another carbon. So this looks like S. The hydrogen is in the back, so this is S. Okay, move to the next one, same thing. Nitrogen gets the highest priority, then this carbon, then that carbon, that looks like S. The hydrogen's in the back, so it is S. Okay, next one, nitrogen, highest priority. Carbon here bound to three oxygens, next priority, then that carbon. Counterclockwise, looks like S. The hydrogen is in the back, so it is S. All right, that is that one. Moving on to question number 14. So we're asked to determine, and what I mean by determine is draw the structure for the following amino acids at pH 2, so very, very low pH. So what you need to do is know the pKa values for every ionizable group in the particular molecule that you're looking at. So this amino acid here is aspartic acid, and we have three ionizable groups: the alpha carboxy, which has a pKa of about 2, the alpha nitrogen, which has a pKa of about 9, and then we have the terminal, the side chain ionizable group, which has a pKa of about 3.5. So at a pH of 2, this is somewhat ambiguous because it's unclear if this is going to be considered fully protonated or not. So the main rule that you need to know here is that pHs less than your pKa, you're going to have protonation. At pHs greater than your pKa, you're going to have deprotonation. So at a pH of 2 with a pKa of 2, you're going to have some protonation, some deprotonation. So I'm going to make the assessment that we're going to consider this completely protonated at 2, just to make the assessment. If this question was actually asked on an exam, you should definitely ask what they want here, because you could use the Henderson-Hasselbalch to determine the exact amount that you have protonation or deprotonation if you had some concentrations. But here we're just going to make the claim that this will get deprotonated. This will get protonated rather at pH of 2. All right, so our structure then, we have our protonated carbonyl, which has no charge, it's just neutral. Then, oops, I drew this upside down, but it's fine. This is going to have protonation nitrogen, which will have a positive charge. And then the carbonyl carboxy group is not going to have a positive charge. So basically the underlying rule here is if you're going to protonate oxygen, it'll be neutral. If you protonate nitrogen, it's going to be positive. Which then implies if you deprotonate nitrogen, it's going to be neutral. And if you deprotonate oxygen, it's going to be negative. Okay, now moving on to arginine. Arginine has a pKa of 2 here. Again, I'm saying that they're all going to be protonated. All the alpha positions are going to be protonated at 2. And this is a pKa of about 12. All right, so what we're going to do then is protonate everything that's possible. So what's going to get protonated first here is going to be the sp2 hybridized carbon there, nitrogen rather, excuse me. The sp2 orbital is mainly what I'm referring to. Because if that happens, then you have extended resonance. I'll just draw one structure, but you also can have this one here, right? But nevertheless, that's why that position gets protonated. Then this will get protonated, the nitrogen here, and then the carboxyl group is protonated, giving that structure. All right, that is that one. Then we'll move on to this one. So again, full protonation. So everything's going to be protonated. Nitrogen is the only thing bearing a charge here. I forgot to give you the pKa values, but tyrosine is about 10, the ionizable group of the phenol. This is about 9. This is about 2. So you would get the following structure here. where you have varying levels of positive charges throughout these three amino acids. So 1 positive charge on aspartic acid, 2 positive charges on arginine, and only 1 on tyrosine. Okay, let's move on to question number 15. So 15 here, we're asked to determine the structure of the following amino acids at pH 12. So now this is extremely basic, so we're going to get deprotonation occurring at many of the sites that are possible. So again, go through the pKa values. This one's about 2, so I'm not going to write pKa this time just to save a little bit of time. pKa of 2, pKa of 9, pKa of 3.5. pKa of 12, again, I'm going to assume at the actual value we're going to get full deprotonation. So this should be clarified with professor if you're when given this exam. But nevertheless, we'll go through this. So 2, 9, this one's 10, this one's 9, this one's 2. So you're going to get deprotonation everywhere. So deprotonation at the oxygen results in a negative charge. Deprotonation at the nitrogen is neutral, so it's going to look exactly like it appears. At the oxygen, again, is negatively charged. So this is the structure. Okay, now let's move on to arginine. Arginine is going to be neutral at the side chain, so no protonation. Deprotonation results in neutrality. The nitrogen here is also neutral, the alpha nitrogen, and then the oxygen will be deprotonated. So only 1 negative charge. Now let's move on to the next one here. So we have tyrosine. So we're going to deprotonate everything. So tyrosine is going to get a negative charge at the oxygen. The nitrogen will be neutral, and then the other oxygen will be negative as well. And this will complete this question. All right, here we have our next set of questions. So we are asked to determine the isoelectric point of the following amino acids. So the isoelectric point is denoted Pi, and it is the pH at which there's an equal number of positive charges as there are negative charges. The Pi is found by taking the average of 2 very specific pKa values. The first pKa value is the point at which below that pKa value, pH lower than that, you will have a positive charge. And then the other pKa value is at a pH above that pKa value, you will have a negative charge. So this is simple in the case when you have amino acids that don't have ionizable side chains, but here that is not the case. We have ionizable side chains. And to determine PIs accurately, you should get the exact pKa values. So on a question like this on an exam, you'll usually be given the exact pKa values. So to aid in this, so I will provide them for you exactly. So this is aspartic acid. So this is 1.95. This side chain is 3.71. And then the nitrogen is 9.66. Okay. So now we have to think about this, right? So at a pKa lower than all of these, we're going to get positive 1 charge because the nitrogen will be positively 1 charge, right? At a pH of 1, for example, we're going to get protonation here, that's neutral. Protonation here, that's neutral. Protonation at the nitrogen, that's positive 1 charge. So let's write this out. So at pH 1, we have a positive 1 charge, which means that pKa 1 in our equation is 1.95. Because at a pH lower than that, we have a positive charge. Okay, now let's move to above that pH. So let's say pH of 3. It's going to be neutral, right? Because we're going to deprotonate this oxygen, but not deprotonate this one. So we'll have a positive, negative, neutral, that's 0. Okay, now at a pH above 3.71, so pH like 5, we're going to get negative charge because we're going to deprotonate this hydrogen on that oxygen and give a resulting negative charge, which is why this is pKa2 now. If we deprotonate further past the nitrogen, we're going to have a total of a 2- charge, which is not any of our conditions, right? That we're going to have an excess of negative charges and not get the isoelectric point. So here the isoelectric point is the average of 1.95 and 3.71, which let's write this out. So this is 1/2 of 6, 5.66. Which is 2.83. All right, now that is the answer for that one. Let's move on to arginine. So arginine, we need, again, the exact pKa values. So arginine, we got 12.10, 2.03, and 9 exactly. All right, so I'm not going to write this one out because we're running out of room here, but pH 1, lower than all of these, we're going to have a 2+ charge, right? Because it's going to be neutral, positive, and positive. We don't want that, right? So then, therefore, pH above that, pH of 5, for example, we're going to have negative, positive, and positive. So that's going to be a total of +1. A pH greater than 9, so 10, let's say, we're going to have neutral, negative, and positive, so that's going to be neutral. So pKa1 then is 9, and that means pKa2 has to be 12.1. So then the average of these two values is going to be the answer. Oops, this is Pi. And the average here is 10.55. Okay, moving on to the next one. So here we need, again, the exact pKa values. So if we look for tyrosine, let's see here, tyrosine's got 10.10. The nitrogen of tyrosine is 9.04, and then 2.24 for the alpha carboxy group. So pH lower than this one, we're going to have neutral, positive, neutral, so +1. So our pKa 1 is that 2.24, which means pKa2 has to be the nitrogen one. And the reason that it has to be that nitrogen one, so let's go above that pKa value, above 9.04. So let's say a 10, right? We're going to have deprotonation, that's going to be negative, neutral, and this is not deprotonated yet at 10. It's not greater than 10.10. So at that point, it would be -1 charge. So because of that, that's where the Pi will be between those two values. So it's 1/2 of 2.24 plus 9.04, which is like 5 point something. 5.64. All right, and that is that one. Moving on here, so now we are asked to determine the structure of the following tripeptide. So this is the same question essentially, it's just that you have multiple side chains to consider. So what you usually do in a question like this is use the pK values that are provided for the free amino acid. So we know the side chain of aspartic acid, which is here, is 3.5. We know that this carboxy group is about 2. These nitrogens are no longer ionizable. This is tyrosine's side chain that's ionizable at 10.10. Then again, none of this is ionizable until the arginine group, which is ionizable at 12.10. And then we know that the nitrogen here is ionizable as well. That's the terminal nitrogen, which is ionizable at about 9. Okay, so let's redraw this structure here. So we're going to protonate here, the oxygen rather, so that's going to stay neutral. I'm not going to draw the chirality just to save time a little bit. We're going to protonate this nitrogen up here. We're going to protonate the arginine group, the guanidinium group on arginine. And then we're going to have protonation at the carboxyl terminus here. Oops, this is incorrect. There we go. And that will be neutral. So this will be the structure now. So right, so we protonation, I forgot the tyrosine. There we go. So that's going to be protonated as well, which has no charge. So this oxygen neutral, this oxygen neutral, and you're going to keep moving along. Tyrosine neutral, and this will be positively charged, and the guanidinium group will be positively charged. So we'll have a total of 2 positive charges. All right, here we're asked to determine a very similar thing. We're asked to determine the structure of the tripeptide at pH 12. So again, let's go through the pKa values. This is about 3.5, this is 2, this is 10, this is 9, this is 12. So we're going to assume full deprotonation here. So this oxygen will be negatively charged, this will be negative, this will be negative, this will be neutral, and that will be neutral, right? So let's draw this structure here. Oxygen's going to be negative. That oxygen's negative. Then we have nitrogen here, the hydrogen, carbonyl, nitrogen, and then the tyrosine. Negative charge. Nitrogen, carbonyl. Let's see here, nitrogen, neutral, carbon, and the guanidinium group, also neutral. So total of 3 negative charge. All right, that is that one. Move on to our next one. Now we are asked to determine the isoelectric point of the tripeptide. So similarly, you need the exact values to do the isoelectric point correctly. So we look at arginine, this is 12.1, the side chain, tyrosine's 10.10. What else? The aspartic acid is 3.71. The carboxyl group we're going to say is approximately 2. Because this is a tripeptide, so the terminal groups vary a little bit. So in general, they're approximated at saying 2 and 9 in the peptide in general, just because you would need to measure it exactly to know what it is. So, but for the sake of these questions, this is what's typically done. Okay, so now we have many pKa values here, and we're looking at finding 2 particular pKa values, right? So to do that, again, you have to go through and think about each pH value to determine what is going to be positive and negatively charged. So let's just start at 1, right? What's the charge at pH 1? So we're going to have neutral, 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 positive, positive. So 2 plus. Okay, so we need to be above this first value for sure. So next, let's go pH 3. That's going to be positive 1. Because neutral, 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 positive, negative, neutral, neutral, neutral. No, that's not right. Negative, neutral, neutral, positive, positive. All right, so at pH 3, it's going to be negative, neutral, neutral, positive, positive. So positive 1. Right? Now above this pKa, so pH of 5, let's say, this is going to be neutral now, right? Because it's negative, negative, neutral, positive, and positive. right? That's 0. So our pKa1 is 3.71. Okay, now let's move on to the next value. So pH 10, we have to go above this pKa value, right? So negative, negative, neutral, neutral. This is still protonated, so positive, right? So negative, negative, neutral, neutral, positive. So that's -1. So that's the next pKa value. pKa2 needs to be 9. So now your PI is the average of these two, and you're done. Oops, that equals, this is 3.71 plus 9. It's 12.71, which is, what, 6.35? Yeah, 6.355. Okay, that is that one. All right, the next question is to determine if the following amine is primary, secondary, or tertiary. This is determined by the number of carbons that are bound to the nitrogen. So here there's only one R group. It's this benzene, so this is a primary amine. Then, if the nitrogen is close enough to an aromatic ring that its lone pairs rather can resonate in, then it is aromatic, which is the case here. The lone pair on the nitrogen can resonate into the ring, like shown, and this gives it the aromatic nature, and hence the answer is aromatic. All right, next we are asked to determine the acid strength here, list them in increasing acid strength. So they're all phenols, we know that much. So they're all pretty acidic right away. So now it's a substituent effects. How are the substituents affecting this? Well, we know that the first one and the third one have either no substituents or are electron donating substituents, which make them worse acids. So those are not going to be the strongest acid. So now we have to compare these two, and by induction, you would say probably the meta nitrophenol is going to be a stronger acid because the withdrawing nature of the nitro is going to affect the OH more than if it's para. But you need to consider resonance because the para here in this case is actually going to have an additional resonance structure that the meta will not have. So let's draw a couple of these to get the point across. Oops, this is negative here, right, like this. Right, so now the negative charge can move onto this carbon. And this is the real key. Right, because now you get this additional resonance structure where that negative charge can become a double bond to that nitrogen, right? So, in conclusion of all that, then 2 has an entirely additional resonance structure than 4. So because of that, 2 is going to be the strongest acid. We want to go in increasing acid strength. So the worst acid is 3 because it has electron donating groups, then 1, then 4, and then 2. All right, and that's that question. Moving on here for the rest of the worksheet, it's just predicting products. So here we have a diene, and this particular diene is subjected to HBr at 25 degrees Celsius. So this is going to be your kinetic product. So we're going to first protonate either of the pi bonds you kind of pick. So, oops. So you're going to get this carbocation as one option. The bromine will then add at that spot under kinetic control. And this will give you one of the products. Then what about the other pi bond? So if HBr is attacked by the other pi bond, you will get this structure here, and then Br minus will attack the carbocation, and this will give you this structure here. And this must be racemic since we started with an achiral material. All right, here we have the same diene, but we're now under a thermodynamic control because the temperature is so large. So let's again undergo the first same step, because that is exactly what's going to occur. You'll form the more stable intermediate. Now you're going to have resonance, because you have sufficient energy to allow for this. Because notice, this is going from tertiary allylic to primary allylic, so this is pretty unfavorable. You're going to need some input of energy. That's what the temperature is there for. Then the bromine can now add, and this will give you your thermodynamic product that is more substituted alkene. This is one of the products. Then, of course, the other pi bond can react. So it will, forming this. Then you'll get resonance again because of the additional energy, which would give you this. And then the bromine can attack this carbocation and give you the other thermodynamic product, like so. All right, moving on. NBS is a allylic and benzylic brominator, so it's going to add a bromine at that position. This is extremely useful because you can now create a very good electrophile for some like SN2 or some other, or maybe even elimination. In this case, elimination is impossible, but the main point is NBS can be used to transform not suitable electrophiles into better electrophiles. Okay, let's move on to 25. So here we have the nitration conditions. Sulfuric acid and nitric acid provides NO2 plus in solution that can be attacked by the benzene. So essentially what this does is sticks on NO2 to the benzene ring. Now this is a strongly electron withdrawing group, so when you undergo Friedel-Crafts acylation, like is the conditions here in the second part of this reaction, you're going to add the acyl group in the meta position. So you're going to get the meta product, and this is all you're going to get. This is your final product. Okay, moving on to number 6. So this is the Wittig reaction. So initially what's going to happen is the phosphorus is going to undergo a standard SN2 reaction with your primary alkyl halide. Then N-butyllithium is an extremely good base. So this is going to remove this proton and stabilize the ylide. Because now remember, phosphorus can have an expanded octet, so this is quite stable. So now this has a resonance structure, which I'll draw because the resonance structure is more useful for showing the mechanism here. Okay, and by the way, an ylide by definition is when you have a positive and negative charge adjacent to one another on a molecule. Okay, so now what happens is this will be a carbon nucleophile that attacks the ketone electrophile in this following way. Okay, if you're wondering how I did that, I will break this down a little bit. So here's carbon 1. This was our carbon nucleophile that attacks carbon 2 here, which is bound to the phenyl group, and the methyl and the O minus now. Now, these opposite charges are in very close proximity, so they're going to quickly attack like that. Again, remember that they can have this, phosphorus rather, can have this expanded octet, which is exactly what's happening here. Now, what happens is you cleave these two bonds simultaneously to form the pi bond, which is your final product. 1, 2, 3, 4, 1, 2, 3, 4. Okay, that's right. So in essence now, if we look at this entire scheme, so on a final, I would recommend you not going through the entire mechanism, unless you have the time. If you have the time, you can convince yourself that you got the right answer. But in essence, you should draw the mechanism to the point that you get the illid. But then once you have the illid, I'll show you a little trick. It's not really a trick, it's just when you understand the mechanism, you can kind of abbreviate it like this. So essentially what's the net change is you're replacing the OH group with this entire carbon group, right? Notice if we look at the final structure, here's that carbon group, you replace the oxygen with that entire group, and then you get this specific alkene product. All right, here's our next set of questions. So again, we're still asked to predict the products. So here we have a organolithium, and this is a very strong base and a decent nucleophile, but we have no acidic protons here. All our alpha positions are blocked. So essentially this is only going to be nucleophilic addition to the carbonyl. That's all that we have possible. Right, again, notice one, this is a carbon 1, that 1 is bound to an ethyl group, and then the methyl group. Now, we of course have protons here, so this is going to get protonated. In this final product. Okay, moving on here, question number 28. So here we have a diene that's electron rich and a dienophile that's electron poor. So this is standard Diels-Alder. So we have this diene that I'm going to draw retaining the stereochemistry, retaining the trans orientation, but drawing it more so it's easy to draw the Diels-Alder. So you have this type of reaction occurring, where you create the cyclohexene now. And when you have outsides on the diene, that is dashes in terms of stereochemistry. And then when you have the inside of the dienophile, that is also a dash. It's the inside. So inside going in the plane, and then outside is out of the plane, like this. Right? So this is the final product, including the stereochemistry, which you need to be very careful here because you can miss some point on stereochemistry. So I'll give you a little tip here from doing these very often. So outside, inside, inside, outside, and then exo and endo. This refers to the approach. So now if you draw this in your final product, outside are always dashed, inside are wedged, outside are dashed, inside are wedged. Endo is dash. Sorry about that. And then what else? So then endo is dash, exo is wedge. Okay, so hopefully that is clear. and useful for you. Moving on to the next question. So here we have sodium borohydride, and we have a compound that has a ketone and a ester. So sodium borohydride is a pretty weak reductant, so something that's relatively stable like an ester is not going to be reduced by sodium borohydride. So all we're going to reduce is the ketone, which is relatively reactive compared to the ester, excuse me. So this is your final product. It has to be racemic because, again, you started with an achiral starting material, so you have to get an achiral product. All right, here we have lithium aluminum hydride. This is a very strong reductant, so this is going to reduce the ketone to the alcohol and the ester to the alcohol, but it will do nothing to the alkene. And water is going to protonate everything. That's why we get to this final product. And again, this has to be racemic. Okay, moving on. Diebol is diisobutyl aluminum hydride. And this is a pretty strong reductant, but it selectively reduces basically anything to a aldehyde if it can. So here it's going to reduce the ester to the aldehyde and do nothing else to the molecule. So this is your final product. Okay, moving on. Oops. 32. This is the Gilman reagent. This reacts at a softer nucleophile. The softest nucleophile we have here is the carbon nucleophile at the conjugated position. So this R group here is going to react in this following way, and then get protonated and reform the ketone. So let's draw this out a little bit. So the CH3 will add here. If you're wondering why you need R2 in the Gilman, I don't exactly know why that's the reason, but you need both dye-substituted cupric lithium or you will not get this to work. So anyway, but you only add one, even though there's two here, only one gets added to the product. Now you protonate this, and then notice this is a enol now. There's no reason that the enol will stay here because it's not stabilized by anything. So you're going to get the tautomerization, giving this as your final product, which notice is chiral now when it's in this form. So again, racemic, must be racemic. All right, and that is that one. So let's move on to the next one here. All right, here we have kind of a review question. So from last semester stuff. So very beginning, we have ozonolysis. So this is going to cleave the 6-membered ring and cleave it to a dialdehyde. 1, 2, 3, 4, 5, 6. Okay. Then NaOH is a strong base. This is going to remove the alpha protons and create an enolate. Okay, then once that happens, now you can have an intramolecular aldol, where this will attack itself, which is electrophilic. This will occur. And now you're going to make a 5-membered ring. So this is where you have to be a little bit careful. So you need to count the carbons here. So the ring is going to be 1, 2, 3, 4, 5 members large. So let's draw a 5-membered ring. And then off of, let's call this position 1 here. So off of position 1, there is a aldehyde that was reformed. Then you have 2, 3, 4, and 5 is now the O. I'm going to just draw OH because that's going to get protonated by the water that we formed in the previous step, right, in the deprotonation event. Now, when you're at very high temperature like this, you can easily form the alpha-beta unsaturated ketone by dehydrating that alcohol to give this product, right? So mechanistically, you would protonate that oxygen, or in this case, we are in very strong base, so you could remove it. You could remove OH as a good leaving group because you're in strong base. When you're in strong base, OH is a decent leaving group. But either way, you need the high temperature, and this is going to aid in forming the alpha-beta unsaturated ketone. All right, here we have our last set of questions for this video. So question number 34, again, is predict the product. So here we have Jones reagent or some variation of it. So this is going to oxidize very harshly all the way to the carboxylic acid. Then SOCl2 transforms any OH to a Cl group. So this will become a chlorine. Then nitrogen is an excellent base and nucleophile, so it's going to attack here, undergo a acyl substitution. Like this. And then you'll get deprotonation. So what's more likely to occur is intramolecular proton transfer here, and then deprotonation of the carbonyl, but this is just as fine because proton transfers occur so quickly, it's not a huge deal as how you draw it usually. Most professors usually don't care, but the reason I mention it here is because the oxygen and nitrogen are so close to each other, it's very possible that intramolecular is going to occur faster than any of this stuff that I'm showing here. But nevertheless, you get the amide is your final product, that secondary amide. All right, moving on. All right, here we have an epoxide and we have sodium azide. Sodium azide is a very strong nucleophile, so it's going to attack the epoxide at either site. It's a good enough nucleophile that you don't really need any acid catalyst or anything for this, but the important thing is you're going to invert the stereochemistry at the epoxide because it's attacking in that way, which backside attack will cleave in this manner. So now if you have N3 attacking the other side, which is possible, you're going to get the enantiomer, which this would be like this. Actually, these are not enantiomers. You can pause here and convince yourself why they're not, but I just realized why they're not because you would number this 1, 2 like this in either case, and you would see that they have the same chirality there. So, well, let's check that actually. So here the oxygen 1, 2, 3, that looks like R. Hydrogen in the back, so it is R. Let's check this oxygen. So 1, 2, 3. That looks like S. It is S, so these are actually enantiomers. Yep, they are enantiomers. So good thing to check. So there's going to be a racemic mixture, is the point. So now lithium aluminum hydride is going to reduce N3 to nitrogen, just NH2 group. And NH2 group down here. So, and then again, we just assess the configuration. So this would be 1, 2, 3. This is R. This one, 1, 2, 3. That's S, but it's R. This one, 1, 2, 3. That's S, so it's S. This one, 1, 2, 3. That's R. so it's S because the hydrogen is in the front. So it is in fact racemic. Okay, moving to the very last question of today's video. So here we have a amide and lithium aluminum hydride. Again, very strong reductant, so this is just going to reduce the amide to a primary amine. And this is your final answer. Again, don't forget that carbon. The carbon doesn't drop here. It's still there. But you do reduce the carbonyl all the way down to just a methylene. So that is all I had for today's video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or any comments in general, please feel free to leave them down in the comment section below, and I'll help you out as soon as possible. So thank you all for watching. Have a great day, and I'll see you in the next one.